Hey class, today we're going to continue on our discussion of quotient groups. And you may remember that in the last two videos, we've always been assuming that the group G was abelian. So now at last I want to consider what this whole idea looks like if G is non-abelian. And in worksheet 29, you already saw that something kind of fishy can happen in the non-abelian case. Namely, if G is a non-abelian group and H inside of G is a subgroup, then this operation on cosets that we've been working with in our last couple of videos, where AH combined with BH is defined to be A star BH, that operation in this non-abelian case might not be well defined. That's bad news because it means that we can't use this operation to turn the set of left cosets into a group, but the good news is that there's a condition that we can put on the subgroup H that gets rid of this problem. Here's what that condition is. It's called being a normal subgroup. So for this, let's let G be any group, possibly abelian, possibly not, and let H inside of G be any subgroup. Then we'll say H is a normal subgroup of G if the following condition holds. For any element lowercase g in the group, and for any element lowercase h in the subgroup, I want it to be the case that G, H, G inverse is an element of the subgroup H. This condition, I think, is pretty hard to unpack at first, so let me give you another way to think about it. For this other way, I'm going to take this thing G, H, G inverse, and I'm going to give it its own name. I'm going to call it H prime, and I'm denoting it with the letter H because, as we see here, our assumption is that it's an element of the subgroup capital H. If we rearrange the equation that I've written in green above, it becomes the equation GH is equal to H prime G. And so another way to state our definition of being normal is that what we're saying is that for every element lowercase g in the group and every element lowercase h in the subgroup, GH should be equal to H prime G for some element H prime in the subgroup capital H. And the reason I sometimes find it helpful to think of this condition in this second way that I've written down is that the equation GH equals H prime G, it kind of looks like the condition of being abelian. It's like being abelian, except it's weaker, because I'm not necessarily saying that GH is equal to HG. I'm only saying that GH is equal to H prime G for some element H prime in the subgroup capital H. In particular, that last comment I made hints at the following true fact, which is that if G is an abelian group, then in fact any subgroup whatsoever inside of G is necessarily normal. Let's unpack why that's true. Well, the original definition of what it meant to be normal said for all G in the group G and for all H in the subgroup H, GH inverse should be an element of the subgroup H. And if I'm assuming that this is abelian, then that's true because I can rearrange things so that the G and the G inverse cancel with each other. So then I'll just be left with H, which sure enough is inside of the subgroup capital H. Or if you prefer to think of the definition in that second way that I mentioned, we can look at it that way too. In that case, what we're saying is that for all G in the group G and for all H in the subgroup capital H, it must be true that GH is equal to H prime G for some H prime in the subgroup capital H. And that's true. In particular, I can take H prime to be H itself, and then GH is equal to HG, because here I'm assuming that G is abelian. So again, by either of these two arguments, we see that if G is abelian, then no matter what subgroup we pick, it's definitely going to be normal. So to make life interesting, let's pick a nonabelian group and see what it might look like for a subgroup of that to be normal. So for example, maybe one of my favorite examples of a nonabelian group would be the symmetric group. So let's let G be the symmetric group S3. Now I claim that if I let H be the subgroup that contains the identity and the cycle 1, 2, 3 and the cycle 1, 3, 2, I claim that that's normal. So to really fully check this, what I need to know is that G composed H composed G inverse is an element of H, where G is any element whatsoever in S3 and H is any element whatsoever in this subgroup capital H. That's a lot of things to check, but let's just check it for a couple of specific G's and H's to get the idea. For instance, I could let G be the cycle 1, 3. That's an element of the symmetric group. It's not in H, but it doesn't have to be. G can be anything in the group. And then I can let H be the cycle 1, 2, 3. Remember, H really does have to come from the subgroup capital H, so I've chosen something in there. And then I do G inverse, so 1, 3 inverse. And, well, actually, one thing you can notice here is that 1, 3 is its own inverse, so I don't really need the inverse symbol there. And then there's a calculation to be done here. You can check my work if you like. I think what you get when you do this composition of 3 cycles is that it comes out to be 1, 2, 3, which, notice in particular, sure enough, is an element of H. Or here's another similar example. I could let G be 1, 2, and still let H be 1, 2, 3. Then if I do GH-G inverse, well, again, G is actually its own inverse, so I can ignore that inverse symbol there. And I've got a little calculation to do. What I think I get in this case is 1, 3, 2, and so in particular, again, that's an element of H, as it was supposed to be. So there's lots more checks like this that I should really do to fully convince myself that H is normal, but this is the idea of how to check that H is a normal subgroup of S3. Now let's compare that to the following non-example. So again, let's let G be S3, but now let's let H be the subgroup that contains the identity and 1, 2. Actually, you might notice that this is the same example of a group and a subgroup that you were studying on worksheet 29. I claim that this is not a normal subgroup. To see why not, I can take my G to be 1, 3, that's an element of the symmetric group. I can take my H to be 1, 2, that's an element of the subgroup capital H. And then I'll look at GH, G inverse. Once again, you can notice here that actually 1, 3 is its own inverse. That's true of any length 2 cycle, by the way. And so when I compose these 3 things, there's a calculation to do. If you work it out, what I think you should find is that you get 2, 3 here. Notice that 2, 3 is not an element of the subgroup H. So we did GH-G inverse, where G was in the group capital G, H was in the subgroup capital H, and the answer we got was not in the subgroup capital H, which verifies that capital H is not a normal subgroup. So let me conclude by reminding you of why I introduced normal subgroups in the first place, and that was so that our operation on left cosets would be well defined. So the following theorem says that, indeed, for normal subgroups, that works. The theorem is almost exactly the same as the theorem that we discussed last video for abelian groups, but now here G is any group. H inside of G, though, is not just any old subgroup, it's specifically a normal subgroup. And the conclusion is the same as before, namely the set of all left cosets of H in G, which is what we typically denote by G mod H. That set forms a group under the same operation that we've been using all along. I won't say much about the proof of this theorem because it's actually almost identical to the proof of the theorem that we did last time in the abelian case, but I just want to highlight for you where this assumption of being normal is being used. So you might remember from the proof of the theorem last time that our big goal was to prove that the operation was well defined. And what that meant was that if AH equals A prime H, then ABH is equal to A prime BH. And now let's just run through kind of the idea of what that argument looks like. It's going to look almost the same as last time. In particular, we start by saying, suppose AH equals A prime H. Remember, that means that A inverse A prime is an element of H. In other words, A inverse A prime is equal to lowercase h for some lowercase h in the subgroup capital H. And then we introduce our element B into the picture. Namely, we look at AB inverse times A prime B, which if we rearrange or unpack it, becomes B inverse A prime B. A inverse A prime we can replace by lowercase h. But now here's the key moment where our assumption of normality is being used. We have B inverse HB, and that by the definition of H being normal is equal to not necessarily lowercase h itself, but at least some element of the subgroup capital H. And that's enough to know that the coset ABH is equal to the coset A prime BH, which is what we need to know that this operation is well defined. So the rest of the proof of the theorem is exactly like last time, so I won't reiterate it. We'll call that the end of the proof of this theorem, and that's the end of this video. So I'll see you in class.